Thank you so much and welcome back. Gosh, we are flying through today's agenda, aren't we? So let's keep moving forward. So for those of you who are interested in diving down into the nitty-gritty of AI, our tech talks are for you. Our first headliner tech talk comes from the VP of AI and Machine Learning at Unity, where he leads efforts around AI and machine learning. He joined from Uber, where he was head of machine learning. And at Uber, he led the efforts to build the world's most versatile machine learning platform to support Uber's hypergrowth. Previously, he was a general manager of Amazon Machine Learning. I'm sure you'll agree that's quite a CV. So, here to talk to us about simulations, the new reality for AI, please give a very warm welcome to Dr. Danny Lange, Senior VP of AI and Machine Learning at Unity. Welcome, Danny. Over to you.
Thank you very much. Yeah, I'm very excited to be here. Good morning on the West Coast, good afternoon on the East Coast. I'm going to talk about simulation for AI. I think that we all known for a long time that data plays a really important role for AI. That's what drives the underlying technology of machine learning and AI. But I think what has come really to the forefront over the last year or so is the challenges, or some of the challenges around the data that we use for AI. So challenges around privacy, using real footage, using images from real people, using healthcare records, etc. It's a big issue. There's also the issue of bias. When you collect real-world data that you use for your AI systems, the real world is not unbiased. The real world is not as perfect as people think. There's also the issue of data governance. We have seen recently a lot of challenges around training AI systems on data, where the data is actually a mix-up of a combination of different data sets, and with a complete lack of data governance, you actually don't know what kind of data you train on. It all often happens that maybe your test data set or your evaluation data set contains the same data that you trained on, which means that you don't really know much when you evaluate your system, because you're going to get a great score even if it doesn't work. Yeah. So simulation offers some very unique opportunities, and the last one I want to mention is maybe also one of the most important ones. It actually democratizes AI, because generating large amounts of data is a way to really lower the cost of AI. It's the ability to build AI systems at scale, breaking the barrier of entry for many companies, and allowing big and small corporations to actually use very cheap data to build the AI systems. So let's get started. Games. I'm coming from a gaming company, a gaming platform company, Unity. We have probably the most popular gaming platform in the world. I think around 60% of all games being made today are being made on the Unity platforms worldwide. Games have been used to drive AI research for a long time. It started 70 years ago with Claude Shannon, who published a paper on having a computer playing chess. It's a very impressive paper. Google it on the internet. It basically outlines a lot of the thinking that is even going on today around the use of AI. Later on, we saw things like Chinook, which was a checkers program that reached expert level abilities. Very interesting system, nicely thought out, with an opening database with basically opening moves, a heuristics driver in the mid-game play, and then a brute force towards the end of the play. Yeah. Later on, when I was at IBM, we did Deep Blue, defeated Garry Kasparov. It was a combination of an ingenious chess algorithm and brute force computing with some of the most powerful computers at that time. Moving forward to IBM Watson winning Jeopardy, a Very interesting system. Hundreds of people curated questions and answers, put it in a big database, and use some nice algorithms to look up the right answer to a given question. And they could, of course, look that up faster than the human participants could remember the answers. Yeah. But there's a pattern here, because up to 2016, with DeepMind's AlphaGo, the idea was to have very smart people thinking out the algorithms and figuring out how to create a solution, an ingenious solution. But with DeepMind's AlphaGo that defeats Lee Sedol in Go, the world champion, in 16, there's a shift. AlphaGo is using a generic learning algorithm. It's using deep learning. And in its first incarnation, it does have a lot of human impact on it, a human design. But what happened further on from AlphaGo to its later variations or generations, like AlphaZero, AlphaZero beat AlphaGo 100 games to 0. And AlphaZero learned to play Go through self-play. So that's a very interesting difference from all the previous systems. Yeah. So with no human interaction, through billions and billions of gameplays, it figures out the strategy to win, and at the end of the day, to beat the system that beat the world champion. So there's a shift here. It's a data-driven shift. Yeah, billions and billions of self-play, and you learn it. So this is what really drives current AI and the future of AI. This has led to this idea of using game engines to generate data has led to a whole swath of various use of various games in advancing AI. We have the Atari games and Doom and Quake, Minecraft from Microsoft. There's a StarCraft effort between DeepMind and Blizzard. It's the whole idea of using these computer games to test new algorithms, to push the limits of AI, because there's actually no cheaper data than the ones that come out of a gaming engine. So what is it with video games that really link them to AI? What is it that makes video games so interesting for AI? Well, let's look at the 4 dimensions to AI. There's the visual component. So if you want to build a self-driving car, or you want to build a vacuum cleaner, or you want to build a safety camera, a security camera that detects, dangerous behavior, visual is the core component here. So think about a single shooter game or first-person shooter game, video game. It's all about visuals. Yeah? It's all about understanding what's going on around you, detect the enemy, etc. Yeah? So video games offer a colossal amount of visual opportunity. Is the second component, the physical. Game engines implement physics. There's gravity, there's collision, there's friction. You can use that if you want to model a robot, or you want to understand the friction of an autonomous vehicle driving on a roadway. Yeah. There's the cognitive aspect. Many video games have puzzles in them, some kind of challenge. You have to find the key, or you have to collect the correct set of items to unlock the next level. Maybe you don't know even what the items are. So there's a huge cognitive challenge in most video games. And finally is the social element. Some of the most popular games today are multiplayer games, where you have to work with other players to solve problems. So there's a strong social element in games, which has a big benefit if you're trying to build AI systems that are based on the multi-agent idea. So think about the game engine in this context. I talked a lot about gaming here. Well, there's the spatial environment. So gaming engines are 3D, 3 dimensions. they have a real-time graphical rendering system. Yeah, so they solve the visual problem, and there's a multimodal sensory system, which is you can have cameras. You can have multiple cameras reflected in that. When you play a game and you see the game, that's like you're watching the game through a camera. You can have different perspectives. You can move the camera, and you can have other kinds of cameras in there that can be infrared cameras, depth cameras, LiDAR, etc. And then you have the physics engine, and in total you have a self-sufficient ecosystem that replicates the real world. So what do you have? Well, with the game engine, you have your private AI biodome. So let's talk about simulation here, and I want to scope this for autonomous systems, and want to talk in particular first about computer vision, and then later on behavior or control, as we call it. So let's talk about computer vision first. So if you look at this video, it's basically moving a camera through a representation of an indoor environment. And what you can see is that you can change the materials on the furniture. And you can think of this as changing conditions in your training data. So this is really just generating data for a system to learn a computer vision model on. Yeah, you have all the objects in the room perfectly labeled. You have the shapes completely expressed, and you can imagine how you will get a perfect set of labels out of this for training your system. Here's an example of a commercial car simulator built on Unity. You can see that we have a LiDAR representation. So you basically drive the vehicle in Unity, and then you generate all the training data. Yeah, just imagine how much more efficient this is compared to driving a vehicle in the real world. Yeah? You can drive in this way. You can drive millions, you can actually drive billions of miles and generate perfectly labeled training data for an autonomous vehicle. Now let's get to behavior, because that's a very important part of this. When you have an autonomous vehicle or you have a robot, one thing is for it to have visual capabilities, to have vision. The other part of it is to actually learn to do something with it. And for that, we use reinforcement learning, which is basically a loop of observe, take action, and then receive the reward or the penalty from that action. And over time, essentially learn from that. It's a trial and error learning method that we know very well ourselves from nature. We use it, humans use it, animals use it. Let me show an example here of a computer learning from scratch. There's a chicken, and the chicken needs to cross the road, and there are vehicles that can hit it, and there are gift packages that it should pick up. Yeah, so the computer observes the pixels just as you do, so it's computer vision, and then it has 4 actions: left, right, forward, backward, and a reward signal. Basically, negative for being hit and positive for gift pickup. And then from scratch, the chicken essentially is moving around randomly, but in a moment you'll see it pick up a gift package up on the right, and then quickly after that getting killed by a car there. So 2 bits of information in 5 seconds, yeah. But after half an hour of training, it actually gets pretty good at picking up gift packages and avoiding the cars. It does get through a few lanes before it gets hit. So it's a good start after just 30 minutes of training. Now watch, after 6 hours of training from scratch, it has become superhuman. These vehicles are coming in all randomly, packages are all random, so every given scene here has never been seen by the chicken before. So it's not like it's cheating. It's basically learned a policy of how to avoid vehicles while picking up gift packages. This is very important. Here's an example. You use the same technology to have 4-on-4 indoor soccer game, and from scratch, these Asians, they learn to play soccer. You see, we didn't tell them to designate a goalie. That's basically something they learn. So the game here is learned from scratch, just as the chicken crossing the road. Yeah. Same here, robot arms, commercial robot arms need to learn to pick up an item. Same technique, learning from scratch through simulation. And at the end of the day, this is what you want to achieve. You want to have collaborative robots that are solving very complex tasks with a great variation. And that's the method, reinforcement learning combined with computer vision. So let's talk scale here. The world is running out of data. The real world is running out of data because all the progress being made is in the area of deep learning, which are by nature very data hungry. We tend to see better results as we feed the systems more data. And what I have noticed over many years now is that we have our own Moore's law for AI, which is that the amount of training data is doubling every 18 months. So we need to look at other ways of getting data. And synthetic data is the answer here. In this example here from OpenAI, they're using a camera to watch the cube in the hand, and then they have a feedback loop where a machine learning model controls the hand. They train this in Unity, generating about 300 billion simulated frames. So 300 billion frames were used to train this hand to do this. Yeah. Move up and look at Rubik's Cube. This took 10 trillion simulated frames. Again, same feedback loop, but what you do is that you train it first in a synthetic environment before you bother taking it to the physical robot hand. So synthetic data is unlocking AI. Think about this, that games, they operate at 30 to 60 frames per second, but with simulations, because we're not feeding a human eye any longer, we're feeding a computer, we can run as fast as we want. Yeah. And think about it this way to get a perspective. Your life at 30 frames per second is 1 billion frames. Yeah. Your life in 1 year is 1 billion frames. So for instance, on Rubik's Cube, when OpenAI used 10 trillion frames, that's 10,000 years of experience at 30 frames per second. Yeah. The fortunate thing is that you can actually increase the frame rate to as fast as a server can handle it, as a computer can handle it. And you can deploy massive parallelism because you can generate the data in parallel. You don't have to run in a single instance. You can run on 10,000 instances, or as in Rubik's Cube case, on 100,000 instances. Yeah. So you also have another thing here that gets into play, which is what we call active learning. You have a training feedback loop that allow you to basically impact the data that you're training on. So lots of possibilities here for generating lots of synthetic data and in very complex environments. Couple of papers. You can snap a picture here. We have a paper on 2 papers on arXiv. There's one from Unity on how to use Unity as a general platform for developing intelligent agents. And there's a very nice paper from Google's DeepMind subsidiary in London using Unity to help solve intelligence. And snap a picture here as well. We have all of what I'm showing you today is available as open source. Emulations for the reinforcement learning component, the perception SDK for computer vision, and the robotics hub, which is basically a set of robotics APIs for Unity. Snap a picture and go and exploit. And that was what I had in store for you today. You feel welcome to follow me on LinkedIn, on Twitter, or connect with me on LinkedIn. Feel free. Thank you very much, and thank you for your time.
Danny, thank you so much. That was wonderful to hear about synthetic data particularly.